Hi there. In this video, we'll be talking about AP Chemistry's topic 6.4, heat capacity and calorimetry. So when we're talking about heat capacity and calorimetry, the first thing we need to understand is that heat always moves from hot to cold. That is an important part of thermochemistry and an important part of this. But the amount of energy that moves from a hot place to a cold place has to be the same amount lost as the amount gained. This is the law of conservation of energy, or also called the the first law of thermodynamics. Those two names are interchangeable with one another. So however much heat a hot substance loses, a cold substance must gain. So when we talk about moving heat from one place to another, we tend to talk about things as the system versus the surroundings. And so if energy is leaving a system is hot and it loses energy to the surroundings, we would call this Q. Q represents heat. And so the heat of the system and the heat of the surroundings. Whenever something loses energy, we call that negative, and whenever something gains energy, we call that positive. So Q system would be negative, and Q surroundings would be positive. So notice negatives and positives can't equal each other. Like you can't say -1 equals -2. But we said the energy lost by the system has to be the same as the energy gained by the surroundings. So we talk about the magnitude. According to the law of conservation of energy, the energy of the system is equal to the negative of the energy of the surroundings. So anytime there's a heat transfer, the system is going to have an energy change. The surroundings is going to have the opposite energy change, but the magnitude will be exactly the same. Another way to say this would be the absolute value of the Q system is equal to the absolute value of the Q surroundings. Okay, so if the system is losing energy from the system's point of view, this would be an exothermic reaction. Because anytime the system loses energy, its energy is exiting the system, and so it's exothermic. The opposite of that would be the surroundings being colder, and the surroundings being hotter, and the system being colder, and heat would flow into the system from the surroundings, and this would be an endothermic process. Again, the amount of heat that the surroundings loses is going to be the same amount of energy that the system gains. And remember, positive means that it gains, so the system's gaining energy. Negative means that you're losing. But the magnitude of these two is going to be exactly the same in this endothermic process, because according to the law of conservation of energy, you can't lose or gain energy in a chemical reaction or a physical process. So the amount of energy is going to be identical here. So every substance, when it gains heat, changes its temperature in a different way. And we call this the specific heat capacity of a substance, which is given the letter C. And this is the amount of heat it takes to change a gram of a substance 1 degree Celsius. Oops, I should put T here, sorry, T. And delta T. So the amount of heat that it takes to change a gram of a substance 1 degree Celsius, change in temperature, 1 degree Celsius. So water has a specific heat capacity of 4.18 joules per gram degree Celsius. And so what does this mean? It takes 4.18 joules of energy to change 1 gram of water 1 degree Celsius. And again, this is for water. Every other substance has a different specific heat capacity. It just depends on the substance. Water has a pretty high heat capacity because water has hydrogen bonds. The water molecules can vibrate quite a bit before they break apart. And so that means they can absorb a lot of heat energy without changing their temperature, their kinetic energy, all that much. So this is actually a fairly high specific heat capacity. Just as a contrast, metals, which change their temperature very quickly when you add heat to them, have specific heat capacities less than 1. So C is the specific heat capacity of the substance. We can rearrange this into an equation that is used quite often Q equals mc delta T. And this equation is useful because if we know the mass of a substance we're heating up, we know the type of substance this is, we look up its specific heat capacity on a chart, like water's is 4.18, and we know how much temperature the substance changes. These are easy to measure or look up, and we can figure out how much heat the substance has absorbed or lost in that temperature change. Remember, delta T is change in temperature, and that's the final temperature minus the initial temperature. Be careful with that because it's real easy to switch initial and final and end up with a negative value when you should have had a positive, or a positive value when you should have had negative. So be careful with that. So this equation is very useful, and we've used it quite a bit, where the amount of heat can be calculated, because you can't measure heat directly, but we can measure it indirectly by how it changes the temperature of a substance. Remember, heat and temperature are different because adding the same amount of heat to two substances changes their temperatures differently. So temperature and heat are not the same. Temperature is a measure of the average kinetic energy of the substance. Heat is the amount of kinetic energy the substance has. Just to give you an example, if I had a small, tiny little beaker of water at 30 degrees Celsius and I had a lake at 30 degrees Celsius, they both have all the molecules have the same average kinetic energy, the small beaker and the large lake. But the amount of heat contained in the lake, if you added up all the kinetic energy of all those molecules, the amount of heat in the lake is way greater than the amount of heat in the beaker. So heat is the amount of energy of all the kinetic energy. Temperature is a measure of the average kinetic energy. Okay, so this is specific heat capacity, which is in joules per gram degree Celsius. We also have what's called molar heat capacity. And instead of being in grams, capacity. It's hard to write and talk. Instead of being joules per gram degree Celsius, it's joules per mole degree Celsius. So just be aware that if they say specific heat, that has to do with grams, molar heat, that has to do with moles. Okay. If you have a higher specific heat capacity, then that means that it takes more heat to change the temperature. You can add quite a bit of heat to something with a high heat capacity before its temperature will actually change. So how is this useful? Well, a lot of times we use this kind of information in terms of calorimetry, which is the way that we measure the amount of heat, or a way that we can measure the amount of heat that's lost or gained by a chemical reaction or lost and gained by a physical process. So how can calorimetry be used? Well, calorimetry is simply a way of measuring how much heat that water gains from a physical or chemical process if we want to know more information about that chemical or physical process. For instance, let's say that I have a piece of metal that is 30 grams. And that 30-gram piece of metal is 125 degrees Celsius. And we want to figure out what the specific heat capacity of this substance is. We don't know what the specific heat is. We don't know what the substance is. So how are we going to do that? Well, what we can do is if we can place that hot piece of metal into a colder vat of water. So let's say that we have 300 grams of water. Excuse me, 300 grams of water, and the initial temperature of this water is, let's say, 28 degrees Celsius. Okay. We also know that for water, if we look up its specific heat capacity, is 4.18 joules per gram degree Celsius, and that's it. So if we take this piece of metal and we put it into this water, what direction will heat flow? Will heat flow from the 125 degrees Celsius piece of metal into the water? Or will the 28 degrees Celsius water have heat flow into the 125 degrees Celsius metal? Hopefully you said that the heat will travel from the metal to the water. So the amount of heat that's lost by the metal is going to be the amount of heat gained by the water. But one of them would be negative. And it doesn't matter which one you set negative, but we'll make this one negative just for them to equal one another. So the heat lost by the metal will equal the heat gained by the water. So this is actually really nice because the metal will lose heat until they reach what's called thermal equilibrium. In other words, a point where they have the exact same temperature. So let's say that we put the metal in and the water heats up to 29.2 degrees Celsius. that means the metal also cools down to 29.2 degrees Celsius because heat transfer will happen until you end up with the same amount of temperature for each of them. That's called thermal equilibrium. So what this means is the heat lost by the metal is going to equal the heat gained by the water. Heat can be calculated by mc delta T, and that will be the heat of the metal. And if we do the water, mc delta T of the water, the heat lost by the metal will equal the heat gained by the water. And all of these things are very measurable. We know the mass of the metal, 30 grams. We're trying to solve for the specific heat of the metal. Change in temperature of the metal, if you'll notice, it went from 125 degrees Celsius to 29.2 degrees Celsius. So T final minus T initial, 29.2 minus 125 gives us negative 95.8. And you need to be really careful with your signs on this. Negative 95.8 degrees Celsius temperature change. Notice that the negative times the negative will end up making a positive on the left side. Let's see about signs on the right side. The mass of the water was 300 grams. The specific heat of water is 4.18 joules per gram degrees Celsius. And the change in temperature of the water, it went from 28 to 29.2, so T final minus T initial is 1.2 degrees Celsius. Notice this is positive on this side, so the negative out in front made the two sides have the same sign. So now, notice we have everything we need to solve for the specific heat of the metal. We just need to do the algebra here, and that's what's important about calorimetry, is the amount of heat that the water gains or loses is the amount of heat that your process gained or lost, just in the opposite direction. So we're going to multiply everything on the right-hand side, 300 times 4.18 times 1.2. We're going to divide all that by the left-hand side, so divided by 30 and divided by 95.8. And when you do that, you get a specific heat of this particular metal of 0.52 joules per gram degrees Celsius. So this is our final answer, and that does make sense for a piece of metal because metals usually have specific heats less than 1. So this is a reasonable answer for our problem. Not only could you figure out specific heats with calorimetry, you could also figure out the heat lost in a chemical reaction called the enthalpy of reaction. So if we did a chemical reaction in the water and the water gains a certain amount of heat, we could figure out how much heat was lost by the reaction. Or vice versa, if the water cooled down, we could figure out how much heat was absorbed by the reaction. So calorimetry is a really important technique, and it all hinges on Q system is equal to Q, the opposite of Q water. If you have any questions about this, please feel free to talk to me. I'd be happy to help you through more of these problems. Good luck.